Before talking about the energy associated with springs, let's do a quick review of forces and some of the things involved with springs. Okay, first, Hooke's law. Hooke's law tells us the relationship between the restoring force and the displacement from equilibrium. And for a spring, this says that the restoring force is proportional to the length that it's stretched and is opposite in the direction of the spring's displacement. So remember we talked about last time that the acceleration and the net force in simple harmonic motion is always towards equilibrium and is always opposite the direction of displacement, and that's what this negative here tells us. So if our displacement is down, so our displacement is down, that means the restoring force is acting in the upward direction, and that mathematical proportion is F equals negative kx. The k is the spring constant, and it's different for every spring. And then our elastic energy equation, which is the elastic energy stored in a spring, is 1/2 kx squared, where again k is the spring constant and x constant, and this is the displacement from equilibrium. Okay, so the further we displace a spring from equilibrium, the more elastic energy stored in it. A couple other quick relationships. The angular frequency of a spring in simple harmonic motion is dependent upon two things: the spring constant and the mass of the thing hanging down from it. Okay, so a larger spring constant, or a stiffer spring, is going to give us a larger angular frequency. A larger mass is going to give us a smaller angular frequency. So stiffer springs mean more force, which means greater acceleration. Larger mass with the same force means a smaller acceleration, so a smaller angular frequency. When we're talking about pendulums, same kind of idea here, except we have g, which is the gravitational acceleration, and L is the length of the string. And you can hopefully see the similarities between pendulums and springs. K is our spring constant, G is our gravitational constant. It's the acceleration due to gravity. If we were to change that, if we were to increase the acceleration due to gravity by increasing the force of gravity, we would increase our angular frequency, but on Earth that's not possible. And then if we increase the length of our string, then it's traveling further, and so we have a smaller angular frequency, assuming that everything else is the same. And so one of the things we can change, one of them stays the same. Man.
Can't make this stuff up. Shim?
Shim. Shim shim. Mr. S just made me die a little inside.
I do that.
He does that.
I know happiness goes to die.
Alright, so as with anything, we have potential and kinetic energy, and we're going to see a lot of similarities between this and other types of motion. Our potential energy in simple harmonic motion is greatest when the object is at its greatest displacement from equilibrium, and the kinetic energy is the greatest as it's passing through the equilibrium position. Hopefully you remember from the previous segment that the equilibrium position, or as the object is passing through the equilibrium position, the object has its highest velocity, and so when something is moving faster, it has more kinetic energy. If something has the highest velocity it's going to have, then hopefully you see that's going to give it the highest kinetic energy. Also, if we remember from the previous set of notes, we can express the velocity of an object in simple harmonic motion, or we can find it at any given point given the equation omega times the square root of x sub 0 squared minus x squared, where, for a refresher, omega is our angular frequency, x sub 0 is the amplitude, and x is the displacement of the object at that point. If we take this expression and we plug it in to our kinetic energy equation for v squared, we get 1/2 m omega squared times x sub 0 squared minus x squared. This gives us an expression for the kinetic energy of an object in simple harmonic motion at any displacement from equilibrium, given that we know the amplitude and the angular frequency, and then obviously the mass of the object. That's not changed. Now, at x equals 0, so when the displacement is 0, when it's at the equilibrium position, the kinetic energy is at its max, and the potential energy is 0. So if we look at the kinetic energy at the equilibrium position, that also tells us then the maximum energy in the system, or the total energy in the system, because that's where all of the energy is kinetic and there's 0 potential. So the kinetic energy max is the same as the total amount of energy, and remember that this expression is minus x squared, but if this is 0, then that expression, or that part of the equation, isn't necessary. So we have 1/2 m omega squared x sub 0 squared, again where x sub 0 is the amplitude or the maximum displacement. Now, if we carry that one step forward, we know that the potential energy then has to be whatever's left over at any given point between the maximum energy and the kinetic energy. So if we say the potential energy at a given point is the total energy minus the kinetic energy, and we plug in here, we can get an expression for the potential energy that's 1/2 m omega squared x squared. And the reason for this is because this part here becomes minus 1/2. If we multiply this through, if we distribute this through, we get minus 1/2 m omega squared x sub 0 squared, which cancels out with this. And then when we distribute it through to the second part, the negative 1/2 m omega squared times negative x squared gives us a positive 1/2 m omega squared x, which is the displacement squared, which is what we have here. So that's how we get to this point from this point. Now, looking at it graphically, and there's numbers on here, but it's just to kind of give you a better idea. The kinetic energy, since the velocity is equal to negative v sine omega t, we can also put kinetic energy in terms of the velocity. And so we plug in negative v sine omega t, and we get kinetic energy is 1/2 m v sub 0 squared sine squared omega t. Idea to see here is that it's very cyclical, just like our displacement, velocity, and acceleration. At equilibrium, the potential energy is going to be 0, and the okay, so then we can see that we're oscillating back and forth between maximum and minimum amounts of kinetic energy is going to be at its maximum. And actually, you know what? Potential energy. And again, we have another expression for potential energy because we know that the displacement at any given time is x sub 0 cosine omega t. We can plug that into our potential energy equation, and let's do that real quick. Okay, so this here is simply the equation that we derived before, right here. But we've plugged this in, and so we get the potential energy is equal to 1/2 mass times the maximum velocity squared times cosine squared omega t. And our two energy graphs together, we should see that the kinetic energy is at its max, where the potential energy is at its minimum. This blue line at the top is the total energy, and notice that the total energy stays the same. And again, this is of course in the absence of any type of dissipative forces like friction and air resistance, as this oscillates back and forth between 2 points. Okay? And that is all there is to that.